Alright, thanks for watching, and today we will evaluate an absolutely beautiful family of integrals called the Malmsten Integral. And it's literally a math adventure because not only is it long, so it's my personal marathon today, but also it'll take us through the beauty of math, like complex numbers, series, Fourier series, gamma function. So it's really like walking in a candy store and you're a math kid. So let's get started. So what is the Malmsten integral? It's a family of integrals that depends on a parameter. Let's call it phi, or theta, or alpha, whatever you want. So not the golden ratio, but any angle between minus pi and pi. And this is the integral from 1 to infinity of ln of x over 1 plus 2x cosine of phi plus x squared dx. So we will find a formula for all those integrals at once, which is really, really cool. And the only restrictions here is that the angle is between minus pi and pi. Because you'll see at some point something will not work if phi is pi or minus pi. And before I do the derivation, I also want to thank Uwe Besel, who came up with a very neat derivation of this. So I just took it from his paper, so it's very, very nice. But just a couple of applications of this. So I really want to show this is super powerful because it turns out one of those integrals I've evaluated in another video, because if you let phi to be pi over 2, then there's no more cosine term. Cosine phi over 2 is 0. So the integral, in this case, pi over 2, it's the integral from 1 to infinity of ln of x over 1 plus x squared dx. And this one might not look like something we evaluated, but I have done it because it turns out if you use the substitution, let's say tangent of theta equals x. So if you actually do that, then you actually get the integral from pi over 4 to pi over 2 of ln of tangent theta d theta, which is actually something that was called the Vardi Integral, which I've done in another video. So this is the Vardi Integral, which is also another cool integral if you want to explore. And we will give an explicit formula for this Vardi integral, but also for other kind of fun integrals, because if theta is pi over 3, then cosine of theta is 1/2. So this integral will be I of pi over 3, which is the integral from 1 to infinity of ln of x of 1 plus 2x over 2, which is x, plus x squared dx. Which is also a beautiful integral to consider. And lastly, if theta is 2 pi over 3, then I think cosine of theta is minus 1/2, and I of 2 pi over 3 will be the integral from 1 to infinity of ln of x over 1 minus x plus x squared dx. So in other words, we'll evaluate all those integrals at once and other kind of fun integrals if you want, depending on your favorite value of phi. Okay, so that was the motivation. Let's now get started with the actual proof. So let's roll up our sleeves because there are 10 steps. So let's do step 1, the warm-up. First of all, even though this integral is already complicated enough, let's make it even more complicated. So let I of phi, we know that is the integral from 1 to infinity of ln of ln of x over 1 plus 2x cosine of phi plus x squared dx. Now, even though this is nice, kind of the problem is the bounds are weird. It's from 1 to infinity. It would be nicer to have the bounds from 0 to 1. And for this, just use a u sub u equals to 1 over x. Then what you get? Well, 1 over 1, that's 1. 1 over infinity, this is 0. And then we have ln of the generous, 1 over u, and 1 plus 2 cosine of phi over u plus 1 over u squared. And then du is minus 1 over x squared dx. So du is minus 1 over x squared dx. So if you want dx, it's minus x squared du, but it's minus 1 over u squared du. So all this thing, it's minus 1 over u squared du. And this is very good because, first of all, notice the bounds here are completely messed up. It would be nice to correct the bounds, but really this minus takes care of that. And then the beautiful thing is, for the denominator, u squared times 1 over u squared, that's 1. U squared times this is 2u cosine of phi, and then u squared times 1, it's u squared. So in the end, you do get the same integral, except the only changes are this 1 over u and the bounds. So this becomes the integral from 0 to 1, ln of 1 over u, which is over, if you want, u squared plus 2 cosine of phi u plus 1 du. And this is really the form we will deal with from now on. In other words, if you want to use a substitution u equals x or something, then the thing that's left to study is the integral from 0 to 1 ln of 1 over x over 1 plus 2x cosine of phi plus x squared dx. So that was step 1. The warm-up, so just rewriting this integral into, well, a slightly more complicated form. We have 1 over x, but at least the bounds are good. Alright, and then for the next part, turns out we would like to use some kind of a partial fraction decomposition, but it's a bit weird because we have cosine of phi, and it's not quite obvious how to factor this out, but I guess in this case, no, it's still not quite obvious, but the thing that saves us is actually complex numbers. So it turns out this real integral becomes something complex, which is very nice. So step 2. Step 2 out of 10. Alright, so step 2. I would like to remind you there's a beautiful decomposition of cosine in terms of complex exponentials. So cosine of phi, it's e to the I phi plus e to the minus I phi over 2, iPhone, and this is e to the I phi plus e to the minus I phi. If you multiply by 2, you get 2 cosine of phi, which is very good because remember, our integral involves 2 cosine of phi. So in particular, it turns out we can factor this out in a kind of nice way. 2x cosine of phi plus x squared. Well, remember, we had this 2 cosine of phi. That is 1 plus x times 2 cosine of phi, which is this, e I phi plus e minus I phi plus x squared. And then notice this is kind of the first part of like a foiling expansion. So, this is kind of beautiful. So it turns out this is indeed the product of two factors. We would like those factors to multiply by 1. So 1 plus something, 1 plus something. And then kind of the cross term should be xe I phi plus xe minus I phi. So try this. xe I phi plus xe to the minus I phi. And it turns out this precisely works because 1 times 1, it's 1. 1 times xe to the minus I phi plus 1 times xe to the I phi, it's this term. And then if you multiply those two, you get xe I phi times xe minus I phi, and those two cancel out, and you do get x squared. And here's why, because it turns out this is a hidden best friend. Because we don't want to expand out this, we want to expand out 1 over this. So 1 over 1 plus 2x cosine phi plus x squared is then equal to 1 over 1 plus x e to the I phi times 1 over 1 plus x e to the minus I phi. And it turns out those two things are hidden geometric series which will expand out. And by the way, so here's what's one I want to say. The next term, remember, to expand something out in geometric series, you need to make sure that things are in the radius of convergence. So you need to make sure those terms are kind of strictly less than 1 for the radius of convergence. But in fact, this is completely legit because what is x to the ei phi? Because we did not choose phi to be plus or minus 1, plus or minus pi, this is actually strictly less than, I guess less or equal, maybe, or equal actually, sorry, that equals to the absolute value of x, but because remember x was between 0 and 1 in the integral, and assuming it's kind of an improper integral, we actually have absolute value of x is less than 1 because we can assume x is between 0 and 1. So in particular, we are in the radius of convergence business. So we can legitimately expand out those two things as geometric series. And this is the end of step 2. And now step 3 is actually to expand that out. So what can we do? We can use indeed our best friend and red pen's amazing signature 1 over 1 minus x. So step 3 is just expand out this product. So 1 over 1 plus x e to the I phi times 1 over 1 plus x e to the minus I phi, that is 1 over 1 minus x e to the I phi, 1 over 1 minus x e to the minus I phi. And then I'd like to remind you, 1 over 1 minus r, that is the sum of r to the n, from n equals 0 to infinity. So indeed, what this becomes, this is the sum from 0 to infinity of minus x e to the I phi to the nth power. So this minus becomes minus 1 to the n, and then x e to the I phi to the nth power times the same thing, but with minus phi. So x e to the minus I phi to the nth power. And if you want an explicit description of this, this is 1 minus x e to the I phi plus x squared e to the 2 I phi minus x cubed e to the 3I phi and the same thing but with minus phi, so 1 minus x to the xe minus I phi plus x squared e to the minus 2I phi minus x cubed e to the minus 3I phi. And this is what's called a Cauchy product, because it's really the product of two infinite polynomials. And what the Cauchy product says, if everything converges, we can actually FOIL this huge expression out. So let's FOIL it out, and in particular, let's see which terms correspond to 1, which terms correspond to x, which terms correspond to x squared, etc., etc. So, well, the only way to get 1 is just 1 times 1. So that's not an issue. How do we get x? There are two ways. You multiply 1 by x, so you get, if you want, so 1 by this minus x e to the minus I phi, or the other way is to expound on minus x e to the I phi, which is 1 times 1. So, to get x, you have minus x times e to the minus I phi plus e to the I phi. Or if one, e to the I phi plus e to the minus I phi. Then x squared becomes slightly more complicated, because one way of getting x squared is to do x squared times 1, so e to the 2I phi. Another way of getting x squared is multiplying x with x, so minus minus becomes plus, e I phi times e minus I phi becomes 1, so plus 1. And lastly, another way of getting x squared is doing 1 times x squared e to the minus 2I phi, so e to the minus 2I phi. And you can check this is the only way of getting x squared, because then we have higher order terms. We have x cubed times 1, that's x cubed, which we don't really care about. And similarly for x cubed, so minus x cubed, so the way to get x cubed is like 1 times e to the 3I phi. And then I guess x cubed, it would be like x times x squared. So e to the I phi times e to the minus 2I phi, which is e to the minus I phi. But so some term is e to the e to the minus I phi, and then symmetrically, I think we have maybe this one. Where did it go? Yeah, x squared e to the 2I phi. No, x cubed. Yeah, x squared e to the 2I phi times e to the minus I phi, which does give you e to the I phi. And lastly, we have, I think, e to the minus 3I phi here times 1, which is e to the minus 3I phi. So plus e to the minus 3I phi. Right. And you can continue this way. Wonderful. I'm back. You can continue this way, and you have higher order terms for x to the 4th, etc., etc. So a way you can write this down is some term a0 minus x times a1 plus x squared times a2 minus x cubed times a3, etc., etc. So this is really of the following form. So this is of the form a0 minus a1x plus a2x squared minus a3x cubed, etc., etc. And the question is, how do we get a? Notice, for a0, it's kind of boring. I think the best illustration is for x cubed. So for x cubed, you start with e to the 3i phi, so in general e to the ni phi, and notice you always subtract 2 from the power. So here e to the 3i phi minus 0, then e to the 3i phi minus 2ei phi, then e to the 3i phi minus 4ei phi, and lastly e to the 3i phi minus 6i phi. So you're always subtracting 2 from e to the ni phi. So what is an? An, it's again what I said, you start with e to the ni phi, and you always subtract 2. So in this case, just multiples of 2, 2k I phi. And you're summing it from doing nothing, k equals 0, until you get e minus ni phi, which will correspond to k equals n. So if you want, this is an explicit formula, and remember here we're kind of alternating, but I'm just worrying about the principal term here. And here's the beautiful thing though, this is a sum in k, so this ni phi, this starting term, we can actually factor out because there's no k anymore. And what you're left with then is e to the ni phi, and then sum k from 0 to n, and then if you want e to the minus 2i phi to the kth power. That would give you e to the minus 2k I phi. Speaking about k's, I hope you're okay, because this is step 3. So 7 steps more to go. But here's a beautiful thing. This is still a geometric series, so we can just, I guess a finite geometric sum. And therefore, we can just use this formula that just says, the sum from k from 0 to n of r to the k is just 1 minus r to the n plus 1 over 1 minus r. So this becomes e to the ni phi, and then 1 minus e to the minus 2i phi to the n plus 1 term over 1 minus e to the minus 2i phi. And what we would like to do is to clean this up a little bit, so it turns out we can actually, not only will this term be real, which is cool, but we can actually write this in a more elegant way. And the way to clean this up, and you'll see in a second why this is true, let's factor out, I guess let's multiply top and bottom by e to the I phi. So it's e to the ni phi of e to the I phi, and then e to the I phi of this term here, so 1 minus e to the minus 2 n plus 1 I phi over 1 minus e to the minus 2 I phi. And it's a weird phi, but... And the reason is you'll see the denominator is kind of simplified quite nicely. And using this, you'll see the numerator will also be simplified quite nicely. So let's put those terms together, and you get e to the n plus 1 I phi times, let's see, we still have the weird numerator, e to the minus 2 n plus 1 I phi over ei phi minus e to the minus I phi. And, well, we'll simplify this soon. But notice also, if we multiply this term by the numerator, this also gets simplified. So this becomes e to the n plus 1 I phi, and then times n plus 1 plus minus 2n plus 1, it's minus n plus 1, e to the minus n plus 1 I phi over e to the I phi minus e to the minus I phi. And here's the trick. Let's divide both sides by 2. And what does that become? This is precisely sine of n plus 1, and this is sine of, sine of n plus 1 phi, and this is precisely sine of phi by the definition of sine in terms of complex exponentials. So this just becomes sine of n plus 1 phi over sine of phi. And therefore, this expression is actually a real expression, which makes sense because we started out from a real expression. We started out from, again, what did we do? We calculated 1 over 1 plus 2x cosine phi plus x squared. We wrote this as a series, and we notice this actually can be written very nicely in terms of sine functions. And notice those are basically constant. You know, the x disappears completely, which is beautiful. All right, so that was step 3. And now let's just rewrite this integral in terms of this beautiful formula we just found. Congrats if you're still alive. All right, so step 4. This one, pretty quick, I would say. So you're just running down the mountain. So what was I of phi? I of phi, I would like to remind you, was our integral from 0 to 1, ln of 1 over x over 1 plus 2x cosine of phi plus x squared dx. And now this bottom thing, we were able to write this as a very nice series because that was the integral from 0 to 1 of this top, ln of 1 over x, and times, again, the sum from from k equals 0 to, n equals 0 to infinity of, again, here an, we had this alternating series, so technically minus 1 to the n, an, and then x to the n, dx. But the whole point is we found a very nice formula for the coefficients. So this integral really just becomes the integral from 0 to 1 of ln of 1 over x times the sum from n from 0 to infinity of minus 1 to the n sine of n plus 1 phi over sine of phi x to the n dx. So our integral, we can write this in this way, and then if you want, it's not always justified, but assume in this case it works. If you interchange the sum with the integral, then what you get is the sum from n from 0 to infinity of minus 1 to the n sine of n plus 1 phi integral from 0 to 1 of ln of 1 over x times x to the n dx. And lastly, what about this term? Notice it doesn't depend on x at all, it doesn't depend on n at all, so we can just factor it out. So 1 over sine of phi. So, to evaluate this I, all we need to do is evaluate this integral and then evaluate this series. And the cool thing is we'll be able to get a closed form formula for it at the end. Now, this term, let's call it Jn. And for the next step, we would like to find a formula for Jn. So we'll build ourselves up. So once we found Jn, we just need to evaluate the series, and then we are done. Okay, wow. The lights are very aggressive today, but let's see. Now, let's simplify our term Jn. And then we're halfway done. I'm guessing this will take more than an hour, but let's see. Hopefully it won't take 6 hours. But step 5. So what is Jn? It's the integral from 0 to 1 ln of 1 over x times x to the n dx. Let's use a u sub in order to transform this into something that's more familiar. And because we want exponentials to appear, let u be this inner term. So release your inner ln. So u equals ln of 1 over x, which is ln of 1 minus ln of x. So it's really minus ln of x. Then what is du? Du is minus 1 over x dx, which tells you dx. It's minus x du, and this is minus e to the minus u du. So you can solve for x in terms of u, and you get this term, so x to the n, so dx will be this, and then what does Jn become? Well, technically an improper integral, so you do it like from 0 plus to 1. Ln of 0 plus is minus infinity, minus minus, it's infinity, and then ln of 1, it's 0, so it's an integral from infinity to 0, ln of u, and then we just saw x is minus e to the minus, x is e to the minus u, so e to the minus u to the n, and we have minus e to the minus u du. And this minus, usually it's bad, but here it's good, because the integral is in the wrong order, but this minus precisely fixes it. And we are left with a nice integral, the integral from 0 to infinity of ln of u, e of minus n plus 1 u, and then du. Which I think looks kind of nicer than that, but still not nice enough. So now we would like to use another u sub. So let v be this, just that, so not with the minus. So if v is n plus 1 u, then we get the following. Nice thing is most things are unchanged, so it's really just a scaling difference. You're still watching, wake up in case you fell asleep. So then the integral becomes, so again, v is n plus 1 u. Look, multiplying by n plus 1 doesn't affect 0, doesn't affect infinity, so we still have integral from 0 to infinity. Ln of u, it's ln of v over n plus 1. And then e of, so n plus 1 u is e of minus v, and lastly dv is dvd, it's dv is n plus 1 du, so du is dv over n plus 1, so n plus 1 dv. But why did we do this? The nice thing is we can just write this term as ln of v minus ln of n plus 1. So if you FOIL this out, right? This is ln of v times e to the minus v and ln of n plus 1 times e to the minus v. We get a nice integral 1 over n plus 1. So this term, integral from 0 to infinity, ln of v e of minus v dv, and minus 1 over n plus 1. This term just comes out of the integral. It's constant with respect to v, and we're just left with the integral of e of minus v dv. Let's deal with this term first, because it's much easier. this thing, it's the antiderivative, it's e of minus v from 0 to infinity. E of minus infinity, it's 0. Minus minus, it's plus. E of 0 is 1. So this term is just equal to 1. Then this term, aha, very interesting. Complicated integral, but the nice thing is I actually evaluated this in a previous video, so I didn't expect that, but it is true. And this one is equal to minus the Euler-Mascheroni constant. So see the video. And the Euler-Mascheroni constant is kind of the difference between the harmonic series and Ln. One or the other, I always forget the order, but the point is you get a finite constant, which is nice, and therefore, what is our Jn equal to? So this complicated integral, which was here, is actually very easy. It equals to minus gamma times 1 over n plus 1, minus 1 over n plus 1, ln of n plus 1, times 1, so 1 over n plus 1 times minus gamma minus 1 over n plus 1 ln of n plus 1, which you can just write as minus gamma plus ln of n plus 1 over n plus 1. So surprisingly, this hard integral we had to tackle is completely settled. It's just equals to this term. So all that we're left is just evaluate that series. So, again, good. We're halfway done, so halfway point. Now step 6. Let us remember what we had to do. So, what was our original integral? What was the original series? So, step 6. I of phi, sorry, that was 1 over sine of phi times the series n equals 0 to infinity minus 1 to the n sine of n plus 1 phi times jn, but we just saw jn, it's minus gamma plus ln of n plus 1 over n plus 1. That was Jn. Now, the minus is kind of annoying. Let's just pull it out. So this one, we'll just put it here. And just like foiling out was useful before, let's also foil out that expression. So this equals to minus 1 over sine of phi times. So let's see, gamma. Gamma doesn't depend on n at all, so we can just pull it out, times the sum from n from 0 to infinity, minus 1 to the n, sine of n plus 1 phi over n plus 1, and then plus the sum from n from 0 to infinity, minus 1 to the n, ln of n plus 1 over n plus 1, sine of n plus 1 phi. Looks complicated. Well, it is, but I just foiled out this expression to get two sums. Now, notice how those terms are similar, at least for the first one. We both have an n plus 1 and an n plus 1. So if you want, just shift the sum by 1 so that you get sine of k phi over k. So if you want let k be n plus 1, well, if n goes from 0 to infinity, k goes from 1 to infinity. And then n would be k minus 1, so minus 1 to the k minus 1. and then sine of k phi over k. That's nice. Also, let's do the same trick here. So this will be the sum from k from 1 to infinity minus 1 to the k minus 1 ln of k over k sine of k phi. What? Just one little thing. Notice if k is 1, ln of k is 0. So really, this sum doesn't start from 1, it starts from 2. And we're not shifting anything anymore. We just say, well, it's the same sum, but from k equals 2. And if you're in doubt, let's just write out those sums explicitly and convince yourself that this is still true. So, in order to evaluate our integral, now all we need to do is evaluate those two things. I guess just evaluate those two sums, one of which I call A, and the other one I call B. And so step 7 will be the study of A, and step 8 will be the study of B. And then step 9 is putting it all together, and step 10 is our answer. So, be strong, you can almost see the light. Except the light disappeared. All right, so. Sorry. So ironic, but. All right, and it's really beautiful. The next step, you might not realize this, but it's actually a hidden Fourier series. Because sine of k, think sine of kx, it's a series with coefficients and sine of kx. It's actually a Fourier sine series. And in fact, it's one of the simplest ones. So step 7, study of A. Okay. So it turns out it is true that the sum from k from 1 to infinity of minus 1 to the k minus 1 sine of k phi over k equals phi over 2. So this would also imply that A equals phi over 2. Why is that true? It's kind of beautiful. Take one of the simplest functions you know of, which is f of x equals x. Consider f of x equals x on the interval minus pi pi. Then we know that f has a Fourier sine expansion. So f of x equals sum k from 1 to infinity an sine of kx. I guess since it's Fourier sine, bn sine of kx on minus pi pi. Now, technically, Fourier series are not always equal. So there are functions for which the Fourier series diverges at every point. But as long as the function is continuous on that interval, we are actually okay. So indeed, on this interval minus pi pi, it is an equality. And this is also why we made sure not to have our phi strictly between minus pi and pi. Otherwise, this fact wouldn't work. Now, if we can write f as this Fourier series, the nice thing is, and there are videos on this I've made, that bn, the coefficients, are just given by the following. 2 over pi, so 2 because it's a Fourier sine series, pi because half the length of this interval is pi, and then integral from 0 to pi of x sine of kx. All right, and here we've done so many integrations. We haven't done integration by parts yet, so let's do an integration by parts. So dx, and that's 2 over pi. All right, anti-differentiate this, don't do anything here. So x of minus cosine kx over k from 0 to pi, and plus, so minus minus integral from 0 to pi So minus cosine kx over k, which is cosine kx over k times the derivative of x, which is 1. So this. But the nice thing is an antiderivative, it's sine of kx over k squared from 0 to pi. But sine of 0 is 0. Sine of multiples of pi is also 0. So this integral disappears. And then the only thing you're left with is, notice, if x is 0, this term is also 0. So you're only left with the term at pi, which becomes, in this case, becomes the following thing then, that equals 2 over pi. And then minus pi, so minus x with x is pi, cosine of k pi over k. But cosine of k pi alternates between minus 1 and 1. So the whole thing then, the pi's disappear, and it becomes 2 times minus 1 to the k plus 1 cosine of k pi over k. Sorry, minus 1, no more cosines, so over k. But this is really the same thing as 2 over k minus 1 to the k minus 1. Because if you want, divide both sides by minus 1 squared, which is 1, and then k plus 1 minus 2, it's k minus 1. So this works. So in particular, what does that say? It says that f of x, which is x, can be expressed in terms of a sine series, k from 1 to infinity, of 2 times 2 over k of minus 1 to the k over k sine of k, sine of kx. All right, sorry. So f of x equals x can be expressed as a sine series 2 over k minus 1 to the k minus 1 of sine of kx. And I think that's all we needed, because instead of writing x, let's write phi. So phi equals sum k equals 1 to infinity 2 over k minus 1 to the k minus 1 sine of k phi. And then lastly, just divide both sides by 2. So divided by 2 and divided by 2. The 2's cancel out, and you're left with sum from k from 1 to infinity of minus 1 to the k minus 1 over k sine of k phi equals phi over 2. And let's just double check if it's the same thing as we wanted. So drum roll, and ta-da! So this is the beautiful thing about Fourier series. It gives us beautiful series like that. So if you sum up those sine k phis, then you do get phi over 2. And the next step is just a fancier version of this, which uses what are called Kummer series. So, which I've also talked about a bit with the Vardi Integral. All right, step 8. Again, just 3 more steps. It's like, woo, you can do it, So step 8. So what was B? So B was like this Fourier series, but with ln. So a sum from k equals 2 to infinity, minus 1 to the k minus 1, ln of k over k sine of k phi. And notice, this is like a Fourier series, but with ln's. And that's why we need those Kummer series, which give us nice Fourier series with ln's. And so I would like to remind you, or I guess if you've never seen this, I would like to present to you the Kummer series. So it involves the gamma function, and you don't need to know much about the gamma function here other than that result with the series, but in case you're curious, it's the integral from 0 to infinity, t to the x minus 1, e of minus t dt. What the Kummer series says is that you can expand out ln of the gamma function in terms of a series 1/2 minus x Euler-Mascheroni plus ln of 2 plus 1 minus x ln of pi, and precisely a series of this form, so minus 1/2 ln of sine of pi x, so that's like the term if you want with k equals 1, and 1 over pi sum from k from 2 to infinity ln of k sine of 2 pi kx over k. I know, you're like, what's the gibberish that Dr. Peyam wrote down? But it's exactly what I said before. It's simply, it gives you a series expansion of ln of the gamma function with those, with sort of like a Fourier series with ln. So ln of k times sine of 2 pi kx. And notice this kind of looks of this form. The only issue is here we have an alternating series, here we don't, but that's not a problem. Turns out we can turn this into this. How? So, here's a cool trick. Choose x such that, because look, this is valid for all x. So let's just choose x such that this ugly term becomes, you'll see, pi k minus phi k. And I guess pi k minus k phi. The k phi comes here, which is good, and this will make this series alternating. So choose x such that 2 pi kx equals pi k minus phi k. And then divide by k, so assuming k is positive, then we get 2 pi x equals pi minus phi k. And then x is just pi minus, k. 2 pi x is pi minus phi, x is pi minus phi over 2 pi, which you can write as 1/2 minus phi over 2 pi. So this gives you x, and then all we need to do in this series, let's write a star, we just need to plug in all those terms, 1/2 minus x, 1 minus x, sine of pi x, and sine of 2 pi kx. So, good. So 1/2 minus x, let's see what this is. 1/2 minus x, well, that's 1/2 minus 1/2 plus phi over 2 pi, so it just simplifies to phi over 2 pi. And then 1 minus x, that's 1 minus 1/2 minus phi over 2 pi, which is very cute. It's 1 minus 1/2, which is 1/2, and plus phi over 2 pi. It's kind of neat. It's like reflection about 1/2. And then, let's see, sine of pi x. What is that? So, sine of pi x, that then becomes sine of, again, pi over 2 minus phi over 2, because x was 1/2 minus phi over 2 pi, so multiplying by pi we get pi times 1/2, which is pi over 2, and pi times phi over 2 pi, which is phi over 2. And the nice thing is sine of pi over 2 minus phi over 2, that's just cosine of phi over 2. So you see, all those terms actually become simplified, which is very nice. And lastly, what about the sine of 2 pi kx? Now, how did we choose 2 pi k? How do we choose x? Precisely such that 2 pi kx equals sine of pi k minus phi k, and that becomes sine of pi x. Sorry. Sine of pi k cosine of minus phi k plus cosine pi k sine of minus phi k. Now, sine of pi k, that is 0. So this term doesn't matter. And sine of minus phi k, it's minus this. So we get minus cosines of multiple of k. It's minus 1 to the k. And times sine of phi k. And what we're left with is minus 1 to the k plus 1 sine of phi k, which is the same thing as minus 1 to the k minus 1 sine of phi k. Because it looks like okay, but it's a phi k. And then we have all the stuff here. We can just plug it into our Kummer series. So star then becomes the following beautiful expression. ln of gamma x, which is 1/2 minus phi over 2 pi, equals, so 1/2 minus x, which is phi over 2 pi. Gamma plus ln of 2. Gamma plus ln of 2. Plus 1 minus x ln of pi, which is 1/2 plus phi over 2 pi times ln of pi. And then minus 1/2 ln of sine pi x. So it's minus 1/2 cosine phi over 2. And plus 1 over pi, the sum from k equals 2 to infinity of minus 1 to the k minus 1 is ln of k, or I guess sine of phi k, ln of k over k. And this is absolutely amazing because what is this term here? It's precisely b. This series, it's precisely the series that we wanted. So all we need to do is just solve for b. So put everything on the left-hand side and multiply it by pi. So if you want, in the end, what do we get? So b equals pi times ln of 1/2 minus phi over 2 pi. And then minus pi, phi over 2 pi times gamma times pi. So minus, phi over 2 gamma. And then minus phi over 2 ln of 2. So let's just expand everything out. And then minus pi over 2 ln of pi minus phi over 2 ln of pi plus pi over 2 ln of cosine of phi over 2. Which is amazing because now we don't have any series anymore. We don't have any integrals because of this Jn business. We don't have any series. So with that, we can actually get a closed form formula for our integral. So what we end up with then is getting pi ln of 1/2 minus phi over 2 pi minus phi gamma over 2 minus phi over 2 ln of 2 pi minus pi over 2 ln of pi plus pi over 2 ln of cosine of phi over 2. I want to emphasize how awesome this is because notice this is a very explicit expression. It doesn't involve any integrals. It doesn't involve any series. And for this, using this term, we can find a closed form for integral. If only there wouldn't be this gamma, because this is annoying. We don't really know what it is, but it turns out we never have to know what this is because we can just, it will disappear. So step 9, and come on, you're almost done. So I phi then becomes, again, so minus 1 over sine of phi times a plus b. Remember, we want a to be gamma phi over 2. And then the other terms were, so plus pi ln of gamma of 1/2 minus phi over 2 pi. So we had this. Then minus phi gamma over 2 minus phi over 2 ln of 2 pi minus pi over 2 ln of pi, and then plus pi over 2 ln of cosine of phi over 2. And now notice the beautiful thing. So the gamma, the little gamma, which we don't really care about, notice it actually cancels out. So we don't even need the little Euler-Mascheroni constant, but what we get then is an expansion in terms of the gamma function, which is all right. And then, just let's clean this up a little bit. So because there are a bunch of minuses, let's put the minus here, and let's factor out the pi's. So it's pi over sine of phi of, let's see, a minus ln of 1/2 minus phi over 2 pi. And then plus phi over 2 pi ln of 2 pi plus 1/2 ln of pi and minus 1/2 ln of cosine of phi over 2. And here's a nice thing. Everything involves ln's. So we can actually write this thing as a big ln. So like a family of ln's. So pi over sine of phi. And then if you do some algebra, you can write this as follows. So this is ln of, so this times ln of, so I guess 2 pi to the phi over 2 pi and then 1/2 ln of pi, it's ln of square root of pi, minus 1/2 ln of cosine phi over 2, it's minus ln of square root of cosine of phi over 2, which becomes 1 over square root of cosine of phi over 2. And lastly, this thing becomes, I forgot the gamma. Where did it go? And then we get 1 over gamma function of this. 1/2 minus phi over 2 pi. So this whole thing is an ln, but the nice thing is there is a kind of nice simplification here. Because notice this is, if you want, square root of pi over cosine of phi over 2. And then I would like to remind you of Euler's reflection formula, which works particularly well here. So it just says, I think, gamma of z times gamma of 1 minus z. It's pi over sine of z or something. Anyway, in this case, Euler's reflection formula says the following. In this case, it says gamma of 1/2 minus phi over 2 pi times gamma of 1/2 plus phi over 2 pi. So if this is z, this is 1 minus z, that equals to pi over sine of pi times 1/2 minus phi over 2 pi. This bottom, it's sine of pi over 2 minus phi over 2. And this is really cosine of a phi over 2. So if you multiply those things, you get precisely this factor here. So pi over cosine of phi over 2. And therefore, all you need to do is take square roots. So square root of that times square root of that and square root of that. So the point is, this term then becomes square root of gamma of 1/2 minus phi over 2 pi times square root of gamma of 1/2 plus phi over 2 pi. And the idea is then, this term here kind of sort of cancels out with this term. So, which brings us kind of to our grand finale. So we see now the goal of the marathon, the finish line. That's what I wanted to say. So step 10. What do we have? I of phi, which is our integral. It's pi over sine of phi. ln of square root. Again, 2 pi to the phi over 2. Phi over pi, sorry. 2 pi over phi over 2 pi. Sorry. 2 pi to the phi over 2 pi, which is square root of 2 pi over phi over pi. I'm so tired now. And this other term, which was, so square root of pi over cosine phi over 2. It's gamma of 1/2 minus phi over 2 pi. Gamma of 1/2 plus phi over 2 pi over, if you want, phi of 1/2 minus gamma of 1/2 minus phi over 2 pi squared, because it's all under this one square root. And now the nice thing is, this cancels out, one of those factors cancels out, and ln of square root, you just put the 1/2 here, so we get pi over 2 sine of phi, ln of, let's see, 2 pi to the phi over pi, gamma of 1/2 plus phi over 2 pi over gamma of 1/2 minus phi over 2 pi. And this, ladies and gentlemen, completes the marathon. Woo! So, this is our integral. And now, of course, you're probably curious, and I'm sure some of you fast-forwarded to the end, what is that expression in terms of the 3 concrete integrals I gave at the beginning? Well, let me show you. So, on the one hand, we had Vardi's integral, which is I of pi over 2. That is the integral from 1 to infinity of ln of x dx over 1 plus, so 2 cosine of phi x, but if phi is pi over 2, then this becomes 0, so 1 plus x squared. And that becomes, again, with phi equals pi over 2. This becomes, look, sine of pi over 2, it's 1. So we have pi over 2 ln of, let's see, so phi over pi, that becomes 1/2, so square root of 2 pi. And then gamma of, so 1/2 plus, sorry, 1/2 plus, in this case, 1/4, I believe. So pi over 2 over 2 pi, it's 1/4. So 1/2 plus 1/4, it's 3/4 over 1/2 minus 1/4, which is 1/4. So it looks, I know the formula looks complicated, but they're basically conjugate terms, which is nice here. And then, what about this integral with pi over 3? As I said, there was the integral of ln of x over 1 plus x squared. This time that is with phi equals to pi over 3. Then it's pi over sine of pi over 3. It's square root of 3 over 2. If you multiply it by 2, you get square root of 3. Then ln of, let's see, pi over 3, phi over pi, it's 1/3. So it's the cube root of 2 pi. And then, so phi over 2 pi, that is, so phi over pi is 1/3, so 1/6. So it would be phi gamma of 1/2 plus 1/6, which is 2/3. And the symmetric part, 1/2 minus 1/6, which is 1/3. And again, if you accept the gamma function, those are closed form formulas. And lastly, I don't know if I wrote the beginning wrong or not, but let's see. So lastly, for I of 2/3, I of 2 pi over 3, that becomes the integral from 1 to infinity ln of x of 1 minus x plus x squared dx. And then with phi equals 2 pi over 3. So sine of 2 pi over 3, it's still square root of 3 over 2, so we still get this. And then we get ln of 2 pi times phi over pi, which is 2/3. And then here we have the same thing. So in this case, I think we have phi over 2 pi, it's 1/3, so it's 1/2 plus 1/3, which is, gamma. 1/2 plus 1/3, which is 5/6. And then 1/2 minus 1/3, which is 1/6. We'll still have this, and this officially ends the marathon. And I'm so tired, but I think it was worth it. So if you like this math adventure, please make sure to subscribe to my channel. Thank you very much. Woo! Now let me see how long this was. It was 1 hour and 20 minutes. Very nice. All right, thank you.